Hi everyone. About the turn of the 20th century, about the same time quantum mechanics was being discovered, Rutherford performed some scattering experiments on atoms, realized that most of the mass of the atom is concentrated deep in its center. The size of the atom is on the order of 10 to the minus 10 meters. The size of the nucleus is on the order of 10 to the minus 15. So this gives you a feel for the magnitude of the concentration of this mass. The nucleus is positively charged, composed of a number of protons which attract the negatively charged electrons which surround it, which then thereby control the chemistry of the atom. So in a sense, the number of protons actually control the nature of these electrons by attracting the proper number of electrons. And so, the hydrogen atom is the simplest atom of all, just one proton, one electron. Helium is next on the periodic chart, and you might expect it to have a mass roughly twice what hydrogen is, because the electron is about 1,800 times lighter than the proton. And so the proton really dominates the mass. So if you have two protons in a helium atom, its mass ought to be about twice as much. The reality is it's about 4 times as much. There's something else going inside the nucleus, and it's called the neutron. The neutron is another subatomic particle, mass about the same size as the proton, but it is electrically neutral. It does nothing. It attracts no electrons, doesn't repel them, doesn't do anything on the electrical side of the book. What that means is that we can have different atoms. So for example, helium normally has 2 protons, two neutrons, so making 4 particles inside of its nucleus. That's what we call helium-4. Helium-3 also exists. That's 2 protons, 1 neutron. And so, and yet we still call it helium. The reason we still call it helium is because chemically it's exactly the same as normal helium. They're indistinguishable. The only difference electrically is because of this mass, and it's the electricity of the atom that controls its chemistry. So these are called different atomic isotopes of the atom. And so you can have different combinations inside the nucleus. Really, the number of protons is what controls what kind of atom you have. Now, another objection to this nucleus idea is that the protons are sitting inside there, but they're all positively charged, and therefore they should repel each other according to Coulomb's law. There must be a second force that's actually holding these nucleus particles together, and that's what we call the strong nuclear force. And it only interacts when the protons get very close together, something 10 to the minus 14 to the minus 15. Once they get that close together, the strong nuclear force starts to come into play and actually overwhelms the electrostatic repulsion, locking the protons together. Now, the strong nuclear force isn't strong enough to attract 2 protons by itself. That's what the neutron does. When the neutron comes along, it also participates in the strong nuclear force, but it has no electric repulsion associated with it. So what it does, it actually helps bring the protons together. Essentially, the protons bind to the neutron, and the neutron holds them together, like it's got 2 hands out. On one side you got 1 proton, on the other side you got another proton, and it's sitting between them, holding the nucleus together. That's helium-3. Now you imagine you get another neutron. That's actually going to support and increase the stability of the atom, and that's what happens. Helium-4 is a very stable nucleus. And so you say, well, let's add a third neutron. The problem with that is that the neutron, by itself, if I just were to hold a neutron in my little hand like this, that neutron actually is unstable and will eventually decay. It will just blow apart into a proton and electron. But when you get a neutron inside of a nucleus, kind of participating in the strong nuclear force, it it doesn't decay like that. But if you have too many neutrons in a nucleus, it starts to act like its old self and will actually decay. And so what you have is this situation where if I were to plot the number of protons in the nucleus versus the number of neutrons in the nucleus, you actually have this island of stability in the center here that kind of runs down the middle, which is telling me that these atoms are stable. And if I have too many protons, electrostatic propulsion blows the nucleus apart. If I have too many neutrons, those neutrons that kind of sit on the outside of the nucleus participate less in that strong nuclear force, which helps support its stability. Those neutrons actually decay. So on either side, the nucleus has a tendency to, it is unstable. And that unstable nucleus is what we call radioactivity.